Okay, then I think we can start. Thank you for coming. I am known for having lots of pictures in my presentations. It's a lot for me as well for remembering what I want to say because I kind of think it through while I choose the pictures and everything. But this one is kind of fun in many different ways. Um, because when I found it, I was looking for something that had something with containers and still had some graffiti art on it. But as you will see throughout the presentation, is that a Chromium-based browser like Vivaldi or Chrome or Opera or Brave is actually consists of many different processes, and you've probably seen that if you looked on your computer. There's lots of processes running, but all together they try to make one single picture. So usually I have like a plan behind my pictures. I just don't tell anybody, but this one I told you. Okay, so we're going to talk about Linux security mostly, but we're going to do it by talking about the Chromium Sandbox. And who am I? I'm Patricia Aas. Currently, I'm a consultant for my own company called TurtleSec. I started my career working for Opera Software, working on the original Opera browser. Then I was a consultant for a couple of years as a Java consultant, and then I went back to C++, which was my main language at Opera, to Cisco, where I worked on embedded software for telepresence systems. And then I went back to making a browser again and worked for Vivaldi, and I did that until last summer when I started off on my own. Oh, and okay, in Norway, I'm also known for making lots of fuss about elections. But, you know, I don't put that up there because I find it embarrassing. Um, okay, so basically, remote code execution is what browsers do. And that is something that we kind of have to think about when you think about how browsers are designed today. Browsers are basically an application that downloads random code from the internet and executes them on your machine. That is the whole concept. And when you get to that point, you realize that how browsers approach security is in many ways quite different from what normal native applications do. Okay, so we're going to talk a little bit about sandboxing, but it kind of breaks down into two types of threats. The one that is the most common and the most focused on in browser security is an external threat. So it's basically this code that you download from the internet. How are you going to protect the user's computer from anything malicious that might be on a site they visit or something? And of course, you also have system internal threats because what your browser contains a lot of your personal information. So mining files, memory, anything system calls related to your browser is something that could yield a lot of valuable information from any kind of malware running on your machine. But we're not going to talk that much about that, but there is a little bit. So the outline of the talk is that we're going to quickly describe the process architecture of a Chromium-based browser. And that's very important because we'll see how that architecture yields how the browser sandbox is built. Then we're going to look at the different kinds of Linux security APIs that are present and used while constructing the sandbox. Then we'll see how that is the construction is done in the initial sandbox, and then later when it is shrunk even further. So first, you have the process architecture of a Chromium-based browser. Now, in my examples here, I'm going to use Vivaldi as an example, but basically any kind of Chromium-based browser will have the same or similar structure, because this is from the Chromium project. So even if you look at Chrome, it will have a similar structure. So we're on Linux machine, so let's go and look for executable files. So you'll find your installation of your browser, and you look for executable files there, and you will find one that is generally named what your browser is named. So Vivaldi, Opera, Chrome, whatever. Often this is a bash script. It's not actually a binary. I think in Opera currently they got rid of the bash script, but very often this is a bash script. And it launches the Vivaldi bin, which is the actual browser binary. And this is something that's very important that we're going to think about, is that you end up with lots of different processes on your computer, but you actually have only one real binary. So all of these different processes are executed from the same binary. There's often another binary as well, which is called, in Vivaldi, it's called Vivaldi Sandbox. This is a set UID binary, and we're not going to talk much about that today, but set UID is like a whole other topic for security. But currently, if you're using a modern distribution, especially like Ubuntu, then this binary is not in use. Okay, so let's see how this kind of develops. So you start off by starting your initial browser binary, and this is going to be what we will talk about as the browser process. And the browser process will make two child processes, one which I call the Zygote init, and this Zygote init will make another process is called the Zygote. Both of these will be called Zygote. So if you look at, well, I'll show you in a bit. And the Zygote itself will make all of the renderers. So you will have many renderers. A render will be roughly equivocal to a tab. But this is a rough estimation, and it's become more and more fine-grained. But that's how you can think of it. The browser process will also yield another process called the GPU process, and the GPU process will often have a GPU broker process. So what you'll see is that you have many different processes, but each one there will be only one of, except for the renderers where you will have many. Now, there are other processes, like for plugins and things like that. I'm not going to talk about that, but the general idea holds for that, but it just becomes more complicated. But basically, you have a bunch of processes. So when you look at it in top, for example, or in PS, you will see that they generally have lots of arguments, but I'm going to look at one specific one, which is the -- type, and that's how you know which process this is. So the Zygote parent process has type Zygote, and the child also type Zygote. So the way you know which one is the parent or the child is in PS, you will see that one is the child of the other one. And then you will have many renderers, and they will have -- type render. The GPU parent will have GPU process, and the child should have GPU broker, but there's been a bug for a while that the broker word is missing, so it's called GPU dash for some reason. Anyway, doesn't matter. Going back, so we're going to look at the Linux security APIs. Now, these APIs are interesting in many different ways. We're studying them in a kind of like a very niche thing where we're talking about the browser sandbox, but the Linux security APIs are more famous for making containers. So if you're thinking, what is the technology behind things like Docker, then that is the same kind of things that we're going to be looking at today. So let's see. If you go to your browser and you type your browser name //sandbox, or in this case Chrome, then you will get this box. Now the box has like one red thing, which kind of makes it a little bit scary, but the rest of the one is green, so it's probably good. But the red one just says that we're not using the set UID sandbox, and that's fine. So the other one says what kind of characteristics are used to make our sandbox. And today I'm going to go through each of these concepts so that by the end, hopefully, you'll know what these things mean. So you have what they call a namespace sandbox, which is basically a user namespace sandbox. Then you have a PID sandbox, network namespaces, or PID namespace, network namespace, seccomp BPF sandbox, and a seccomp BPF sandbox supports tsync, which is it should have done because it basically means, well, we'll look at that in detail later. And then YAML LSM enforcing. Okay, so first we're going to look a little bit on how these things interact. So this little web thing here is a web page, so it's inside of your renderer. So you have something that you're rendering from the internet. So the first thing that you can see here is that we'll surround it in what is called a network namespace. network namespace in the context of this is something that will isolate this process with regards to networking. In the case of Chromium, that's basically no access to the internet at all, which is kind of interesting because you're rendering a web page, right? And to facilitate that, you actually have piping of networking information from other processes to this process. So this process in itself cannot connect to the internet. When you're looking at this more in a container structure, you will generally have ways of manipulating your network namespace in different ways. So you might have one container be able to talk to another container, but not be able to do other things. But in this case, it's basically you're cutting off access to the network. Then we surround that again with a PID namespace. Now, a PID is a process ID on Linux. And when a process is inside of a PID namespace, it cannot see other processes on the computer. And this is, again, you kind of might recognize this from being inside of a container. It looks like you have the machine to yourself. But this is a virtual world, and this virtual world is made in part by these namespaces. So from the process's perspective, it is the only process here, and it has PID1. So the first process that enters a PID namespace thinks it has PID1 and it is all by itself. In reality, outside of the namespace, it has a real PID that is not one. But from inside, that's the view it gets of the world. And both of these are inside of a user namespace. Now, if you enter a user namespace, inside of that namespace, you will think that you are root. This is kind of cool, and one of the things that is leveraged actually to make these other namespaces is that idea, because many of these capabilities you have to be root to do. But you are not root, you're not running as root, so how can you do things that require you to be root? And one of the things that happen in modern Linux distributions is that you can create a user namespace without privilege. So you don't have to be root to create a user namespace, but once you are inside of a user namespace, inside of that little world, you are root. And that suddenly opens up the possibility of making network namespaces and PID namespaces and things like that that usually require privilege. Then you have a set R limit to limit some access to resources like memory and things like that. We're not going to talk too much about that. Then chroot is used to cut off access to the file system, and I'll show you a little bit about how that's done. And then you have seccomp and capset, which are used to cut off access to the system calls. So this is sort of what we're going to go through today on how this actually looks in code. So if you have the initial sandbox, or if we go back, here. So this is the structure of the applications. These are the running processes and their parent-child relationships. So since there's only one binary, you need some way to create these processes. Because you have one binary and you have to re-execute it in some way several times to create all of these different processes. And that's done in two different ways. So you can do it with a clone, and we'll talk more about what a clone looks like. It's even for people who program a lot of platform stuff on Linux, they're often not used to talking about clone. But it is quite a cool concept, so we'll look at how that looks like. But the more normal thing you do is you fork a child process, and that is also done here. So sometimes clone is used, sometimes fork is used, and it's generally based on whether or not you need the clone, because it provides more control over how this child process, what the child process will have access to and how it will behave and how it will relate to you. Okay, so the initial sandbox I call is when the browser sets up these two child processes. So we'll look at how that is done. So fork exec is the normal or the common way of starting a new application on Linux. Basically, in a fork, if you call fork within an application, fork is a very simple function. It takes no parameters and returns an int. So it's very simple. So if you call it, then you will make a duplicate of this process. So it will be exactly the same. Memory will be the same, everything will be the same. The only difference is that in the two processes, you will both be returning from this call. You'll both be returning from fork. And how you distinguish if you're the parent or the child process is the return value of fork. So if you are the parent, you will get the PID of your child. Yeah. One of the things that you could do after you've done a fork is that you will say, okay, I made a copy of the process, but that's not exactly what I wanted. I wanted to run this other program, this binary on disk in this process instead. And then you generally say, okay, I want to exec this binary. And then you'll do the exec, which will replace everything in the process. Now you're replacing all the memory, all the stack, everything, and you're just starting from main like a regular application. And this idiom is usually called a fork exec. Yeah. Clone is similar to fork, and actually very often clone is how fork is implemented. But it takes a lot of arguments, and it behaves in a little bit of an interesting way. It gives you a very high degree of control over this new thing that you create. And actually, clone is so powerful. It's used for many different things. So, for example, if you want to make a thread on Linux, it actually uses clone. It passes some kind of different kinds of flags to clone, which says, I want this new thing to share my address space, for example. And suddenly now you have two different processes, threads, tasks, whatever you want to call them, that share the same address space. And there's a bunch of different flags that are used when you want to create a thread. And we're going to look a little bit at that later. Okay, so the sandbox in itself is constructed in stages. And to do that, you have to find opportunities from when you can actually introduce these barriers. Because you want to, especially let's say that you're doing it for the render process, you want to make sure all of the barriers are in place before you start executing some kind of random code from the internet. So this is generally done at startup as the process starts up and as it creates these child processes. So if you're using fork, you basically have two opportunities to do something. Is before you call fork or after you call fork. It doesn't really give you a lot of opportunities to do something, but if you have something that applies for both the child and the parent, you can do it before the fork because then the child gets it automatically. If you want something that only applies to the parent or the child, then you do it after. But if you combine it with an exec, then you have a little bit more, right? So you have before the clone and the exec like before. Then you have at clone. If you use clone, then you can pass a bunch of flags to clone, which will give you some of these policies. Then you have this little period of time that after you've created the process, you're still copies of each other, but before you do the actual exec, you have time to do stuff. And that's a good time to do many things that you, because a lot of things are inherited by your child. Like if you do a fork, it's basically everything, right? But even if you do an exec, you can do things like getting file descriptors and things like that you might not want the child process to have. So this is your time to like close whatever you don't want. Especially like if you look at this, often the child wants to communicate with the parent. And so the parent will open pipes so that they are available for the child. But when the child gets it, the child wants to close the end they're not using, and the parent wants to close the end that they're not using, and so they end up with one end each. Stuff like that. And then you have, on actual startup, then you have ways of communicating with this new process, because now you're basically loading a new binary in, and you want to communicate with it, but it's a little bit limited what you can do. But you do have the environment where you can add stuff, and then you have arguments. So we'll look at the first part first, right? So I talked about namespaces, and I said that they limit what you see. And how do you create the namespace? You do it at clone, or there's another system called unshare, which you can also use. But unshare is different than clone because it basically moves this process that calls unshare to a different namespace. So in the sandbox, you have basically three types of namespaces in use. You have the user namespace. Now, if you look at up here, the clone underscore new user, that is the name of the flag passed to clone. So they have this clone underscore something. So you have the user namespace, then you have the PID namespace, and then you have the network namespace. And yeah, so you pass these flags to clone, and that will define the namespaces that the new process will be inside. So inside of Chromium, you will have lots of test code. Now, this is one thing that's kind of interesting about something that has to be highly portable, like a browser. You basically cannot make assumptions about what kind of distribution, how old, how new, what is available, what kind of flags the Linux kernel was built with, all sorts of things that you don't know. So there's a lot of code in Chromium which deals with testing and seeing what is available, and also testing and seeing if something is broken, and also then if something is buggy or as a known bad version, to bypass them. And this is kind of interesting because let's say that you are, and one thing that often happens on a Windows machine, for example, you've had problems playing a video, or it's Yankee and it's just not a good experience. And then somebody will say you should update your driver. And you go like, okay, well, I'm updating my driver, my graphics driver, and that's going to help my video performance. But actually, probably inside of Chrome, the Chrome has just noticed that your driver is known to be buggy. It has bypassed it and is now doing software decoding on your machine. So you update your browser, your driver, Chrome will notice that you now have a good driver, and it will go to hardware decoding of your video. And there is so much of that throughout the code base, checking and seeing. So with regards to creating namespaces, it basically gives it a shot. It creates small namespaces just to see if it works. And then it will take as many as it can and create the sandbox. But this also means that the sandbox and how solid it is will depend on your machine and what is available there. So if you have an older machine, then you might not be as protected as you have, or if you have an older distribution, you might not be as protected as you would be with a newer distribution. So it's basically using what is available, and if things are not available, it's not in use. The interesting thing about Clone, and it has like a weird interface, inside of Chromium, they've actually made a wrapper around Clone, which emulates the interface of Fork. It's probably because Clone is not well known for programmers, and so it's easier to have something that behaves in a way that programmers are used to. Yeah. So this is the code that emulates the Fork. So here you can see that you have, generally you'll see when I put code on the slides, it's basically exactly the code as it is inside of Chromium, except I've removed all comments and all error checking because I have to fit it on a slide. So here you will see that you make this flag where you're ORing these different kinds of namespaces that you want. And it's using a sort of esoteric thing that people don't use much anymore, which is set jump. It's going to do a long jump. Are anyone familiar with a long jump in C? No. Okay. So a long jump is kind of weird. It's basically, okay, how many are used to goto? Have you heard of gotos? Okay, awesome. Okay, as a long jump is like a goto like on steroids. So in a goto, you can basically jump to a different place in the same function. With a long jump, you can jump anywhere you want. So you can jump way down the stack. And so it's not much in use because, you know, there's issues with this. You're skipping returning properly, and that might skip releasing resources in a proper way and things like that. So nobody actually uses it normally. But this is how it's done. So you create this jump buffer. And here is the jump buffer env, and it's allocated on the stack, and it will store all sorts of like interesting information about where you are on the stack. And this information is later going to be used to try to jump back where you are now. And then you do set jump here. So basically bookmarking this location. This is where I want to go back to. So later when I call long jump with this buffer, I want to come back here. And then it calls clone and long jump in child. And this is very indicative of how the Chromium source code is. They like names that look like sentences, right? But you're passing this jump buffer into this function and also passing the flags. So when you come in there, this is where we're actually going to do the call to clone. And one of the things that you might notice here, which is kind of weird, is this the stuff in turquoise. It's creating a stack, because clone will not make you a stack. It's kind of weird, but that's how it is. And so you kind of have to make a stack yourself. And then you pass in a pointer to that stack to clone, and clone will set up the new process to use this stack. You're also passing in the flags, and you're passing in this environment buffer. One of the other things that you're passing in is this clone helper. Clone helper is a function, and this is the reason why people often don't use clone, I think, without taking the stack thing is weird. But it is also the fact that, as I said before, if you call fork, it's simple. It has an int return value, takes no parameters. Both processes return at the same point. It's very understandable. With clone, that's not the case. The child process will not return from clone. The child process will call this clone helper function. So the parent process will return from clone, but the child will call this function instead. And so this is what we're going to use long jump for, is to simulate it so that the child also returns from clone. Because if you look back here, we set the bookmark, the set jump, we set it there. So what we want is the child to jump back there afterwards. Okay, so let's look at clone helper. Clone helper is very simple. So it takes this void star argument, which is our jump buffer, because we passed it. Let's see, I'll go back. So we passed it in as the fourth argument, clone, and that's going to be passed in as an argument to clone helper. So we get our jump buffer in there, and then we basically do just a long jump to it. We don't do anything else. We just want to jump back so that we look like we return as well. And then there's an assert false and return 1, but that is unreachable code. Okay, so that's a neat little trick on how to do a clone without actually having to bother all your colleagues with your weird clone. And you got a cool look at using long jump for something, which nobody does. Anyway, so then you have unshare, which is used once in the Chromium source, and that moves, like I said, the current process into a namespace. And it is used in one place as basically a test, can create process and new namespace. So it's basically, again, like Chromium has a lot of these, like try to do something, see if it fails. If it fails, then we're going to try something else. Okay, so then we're going to look at before exec and at startup. And there's a lot of stuff, and especially in Chromium, which is very complicated. Since you have all of these different processes, you have like gazillion pipes, you have lots of inter-process communication. It is insanely complicated. And because of this, there becomes a lot of cleanup that has to be done. So I'm going to list them up, but it's probably for normal application not very interesting. So you fix the environment. You might take stuff away or alter something so that you make an environment that is the way that the child should see it. You fix your file descriptors, maybe close some. Fix your signal handling, because what happens if you have a signal occur in the child process? How should that propagate? You can set up process groups, maximize resource limits. Then you have this PR set no new privs, and we're going to get back to that later because that's kind of important. Then you might change your current directory and then select the executable path. So lots of stuff, and then the command line. So basically, lots of things that you can do after you created the process, but before you do the exec. Okay, so we've created these two child processes, the Cygot init and the GPU process, using fork exec or clone exec. And what you'll see is that the Cygot init is created with clone and is added into a user PID and net namespace. But the GPU process is not. The GPU process is just forked. And the reason for that is that the GPU process is inside of Chromium, the only process that is allowed to communicate with the GPU. And that means that any kind of driver libraries and things will be loaded into this process. And GPU libraries are generally extremely needy. They need a lot of access to your machine. So the GPU process doesn't have a lot of protection in that area. But as you can see in the box, it says seccomp, so we're going to look a little bit at seccomp, which is used to do some sandboxing of the GPU processes. But the Cygot init is inside of a user PID and net namespace, which means that their its child processes will also be that. And later we will make that even more restrictive. So I said that we'd look at the PR set no new privs, and that is basically because if you want to call seccomp today, which we'll look at in a little bit, you have to set it. This one does a little bit of a cool thing. It's to protect against many types of security vulnerabilities, which has to do with escalating privilege. So in this case, you're basically saying that you can't get new privileges by, for example, executing a child process. So any kind of thing that would normally give you more privilege than you have will fail or not grant them. And so this is something that once you've set it, you can't take it back. Okay, so then we're going to look at seccomp. Now, seccomp is really cool. Seccomp is filtering of system calls. And it is extremely, extremely powerful. So if you can when you set up a seccomp filter, you basically can whitelist or blacklist, however you want, all of the system calls that this process makes from now on. And this is actually repurposing of a part of the Linux kernel, which is kind of interesting. Seccomp BPF. The BPF part is called Berkeley Packet Filter. And it was actually made a long time ago to filter TCP packets. So this is a language where you basically write a program and you install this program in the kernel. And the kernel has this like tiny little virtual machine running this program. And whenever, in the original version for packet filtering, the kernel will say, okay, I have a TCP packet. Should I pass it to this application? And it will run the little program, say yes or no. If it is a yes, it will pass it up to the user space. But this passing through the user space, kernel space boundary is a very expensive operation. So you only wanted to do it if the application really cared. But what you ended up with this kind of functionality is you had a tiny little VM inside of the kernel that can run programs for you. So this is as something that recently has been more and more repurposed to do different things. And in seccomp, that is what it does. You make this filter program, you install it in the kernel, and whenever this application does a system call, then this program will be exercised to say, how should we handle this system call? And you have many different things that you can do. You can deny it, you can fail, you can say exactly how you want to fail. You can also inspect arguments. So you can say, okay, it should succeed if the third argument is null, but if it's not, then, And you can do this for all of the system calls. So you can also default. So it's more like a switch. So it's like if you pass through and none of it hits, you can say, what is the default you should do? Like, should you default allow something or just default deny? Very often it's used as a default deny. So this becomes a whitelist. So anything mentioned is possible it could pass through, but if you don't find it, you're going to deny it. So it is not very user-friendly, okay? If you look at this on Mac, they have this like fabulous language. It's like a text file. You will go like, it's readable, it's understandable, and it has the same kind of function. This is not. This is a bytes in a buffer with a void start pointer you're passing to the kernel. It's not very user-friendly. The user-friendly interface is a bunch of macros that you can use. So what often happens that people build something more user-friendly on top of it. And inside of Chromium, that is basically some classes that wrap this. Yeah. Now, when we saw the Chrome Sandbox thing, there was one that said seccomp BPF with tsync. And tsync basically only says that any seccomp program installed in this process applies to all of the threads, not just the thread that called seccomp, but all of the threads. Okay. So inside of Chromium, as I said, this is more, it's abstracted a little bit. So basically they have what they call a policy, which is a class. So you make an instance of this class and you have different types of classes defining different kinds of policies. And these classes basically have a switch. Well, okay, when I say basically, they have a switch. So they have a function, which is basically a switch, where each case is a different kind of system call, and you can handle them in different ways. And if you fall through the entire switch, it's deny. And the fact that it is a whitelist is kind of relevant, because if you have an extended policy, if you take this class and you subclass it, then you are adding stuff that is allowed. So you are extending the policy, you're making more things allowed. So the further down you go, the more permissive it is. So you have the baseline policy, it has a child class called GPU process policy. That one has a GPU broker process policy. So what you'll see is that, okay, so the GPU process is more restrictive than the GPU broker process. And then you have the renderer process policy, which is separate. Okay, so what does this look like in real life? Like, if you want to look at the code, I have the actual files underneath, so you can go and look inside of Chromium. But this is basically what it looks like. So you have start sandbox with policy, where you're passing in this pointer to a policy object. Then you create this sandbox BPF, passing the policy as the argument, and then you call this function start sandbox. Start sandbox does nothing really interesting except call install filter. And when we come to install filter, the whole like high level C++y stuff kind of breaks down, and it looks like this. So it does this program assemble filter, which will then try to take this switch and make this binary representation. And then you're copying this binary representation into this structure, the sock filter on the stack. And then you're just passing, mem copying your program in there and passing it to seccomp. So seccomp is, so there you see the PRCTL set no new privs. They do it a lot of times, but it's basically not needed to do that many times. But I guess they're just afraid they'll forget. So, but here it's very important to do that before seccomp, because if not, you can't do seccomp unprivileged. Yeah. So then it passes some arguments to seccomp, amongst others, tsync. And this is also one of those cases where if you have an older version of Linux, then it might not have the seccomp call. And so then it'll use an older version, which might not support all of the same things. So again, it has to do with how updated is your kernel. Okay, so then we're going to look at chroot. And chroot is probably the most famous of all of these APIs, and mostly because it became famous for jailbreak things on Mac especially. But it's used in a kind of cool way to make the Chromium Sandbox. So basically, chroot has to do with what can you see of the file system. That's basically what it is. Set what is the root directory for this process. So you can set it to any kind of arbitrary folder, and then if that does cd slash, it will end up in that folder, even though that folder is not slash. If you can see like a pattern throughout all of this, it's a lot about lying to the running process, right? It's like saying, yeah, you're root. Yeah, you're PID1. Yeah, this is the root folder, right? But it has basically to do with the idea of a browser sandbox today is basically that, yeah, we're going to do all of these security things inside of this process, but if you manage to break out of our process in some way, if you manage to break out of the JavaScript virtual machine, and you break out of the process and you get access to the system underneath, the world that you see is very uninteresting. So this has to do with the layered security, right? And this has become much more common in all sorts of other applications today, is that you have, previously you thought, okay, I have perimeter security, right? I have my firewalls and everything, and inside of that I'm safe. I don't have to worry about security. But we're moving beyond that. Yeah, I'm going to keep my perimeter security. Yeah, sure. But I'm still going to be looking inside. I'm going to try to isolate things even inside of my own network, because if somebody gets inside, I want to be able to control what they can access. Okay, so the way they use chroot is really neat, and they use the clone again. So let's see. So the idea here is that we want to drop all access to the file system. And we're going to do that by calling clone again, but with this flag called clone_fs. And then clone_fs is kind of interesting because it shares file system attributes with the child. And in this case, it shares two interesting properties. I will make a child process, and it will share my current directory, and we will share what is our root directory. So both of those things are shared. So if one changes, let's say that the child changes directory, then the parent will also change this directory. Or if the parent changes its directory, then the child will change. So they will move together. And that is used specifically here, because the child will chroot to a process-specific directory. Then immediately after, it will change directory to slash, to its root, which is now the process-specific directory it called chroot with, and after that it will just exit. This is very interesting because what you will see is that, okay, so you have a parent process creating a child process, and then inside of the child process, it will chroot to a process-specific directory. This is a directory that is specific to this process, to the child process. And right after, it will do cd slash. So now both the parent and the child, their current working directory is this child-specific directory, which is this /proc/self/fd-info. But then immediately after that, the child will exit. This means that now the parent process has been chrooted to a directory that no longer exists. And suddenly you have a process that no longer can access the file system. It's kind of cool. Looks like this. Same thing as before. You have to make your stack. In this case, you're passing clone_fs and then the sigchild as flags. You have again this function that the child is going to call, and then the parent is going to wait for the child. So when the child runs, it will do the chroot to this process-specific directory. It will change directory to slash, moving both the parent and the child to this directory, and then it will exit. It's a very neat trick. But basically, like I said in the beginning, you have the namespaces, so it will limit what you can see from the system. But in this case, with the chroot, it will also limit the access you have to the file system. So this process will no longer be able to access the file system. It won't access the network. It will think it's PID1, and it will think it's root or something similar. You might want to change it. Then we can talk about capabilities. Capabilities used to be very important. The problem is that Linux capabilities it became too much. For capabilities basically says how privileged you try to split up the idea of you have something that is root and you have something that's not root by saying, okay, you have something that's root, but I'm going to give it some extra privileges, some extra kind of roles if you want. The problem is that you ended up with this massive role, which is called capsysadmin, which is basically anything interesting you needed capsysadmin, which was basically root. And so it became like, it doesn't really work really well, in my opinion. But one of the things that you see is that you can drop all of the capabilities you currently have. So that's one of the things you might want to do as you move through this process of trying to make this sandbox smaller and smaller. Is like, okay, any kind of capabilities I currently have, I want to lose them. I want to become totally without any capabilities. And that's done in this credentials drop all capabilities. Another thing that you can do, which is also done, is set resource limits. Now, this is also kind of like an old API. So set R limit, basically, in this case, it's used to see, I don't want this process to have more than this much virtual memory, things like that. Today, what is more used, let's say in containers, is things that are called C groups. We're not going to talk so much about C groups because in a normal desktop browser, C groups aren't used that much, or not used in Chrome or Chromium. But if you run Chromium on a Chromebook, like I have here, they do use C groups. And C groups then is used for kind of cool things, because Chromebooks are very low spec devices, or now you have like high spec Chromebooks, but in the original ones, low spec. Basically, you have like a cell phone chip inside of something that pretends to be a laptop, right? And so the resources it has very limited resources, and how can you use that? Because what you know from desktop is you're running Chrome and it basically takes all of your RAM. It's like you thought 16 was good. Chrome will leave you too. And so what they did running Chromium on Chromebooks is that they basically said that each tab is a C group. And what you can do is, you might have seen with containers, is that you can do things like you can freeze a container, move it to a different server, and then thaw it, and it will start running exactly where it was. Okay, so now you can think of, okay, so I can freeze all of the background tabs so they no longer consume any resources. But if you switch tabs, then I will thaw them again. And this is a way to very finely grain control your resource consumption. But this is something that is very close to the metal. It's very difficult to control if you don't have control over the exact hardware and kernel version and things like that. And so it's not very portable. But of course, Google makes these Chromebooks or cooperates with people who make Chromebooks so they can do these testing and make sure that it works. But there is code for this inside of Chromium. So it might be interesting if you want to run Chromium on an embedded device, for example. Yeah, so set R limit is like the poor man's version of this. You could do some things. You can set the maximum size of the data segment and maximum size of the virtual memory. So this box here, with the Cygot init, the Cygot and the renderer, has now been shrunk even further. So it was already in these namespaces, but now it has no access to the file system, and you've dropped all capabilities, and yeah, and then you set resource limits. So basically, you're just trying to shrink and shrink and shrink, because what you are trying to protect the most is the render process. Most of these other processes are fine, because they're your own code, you're running your own code, you're not running anybody else's code, you're fairly safe. But still, they're sandboxed, right? But the render process, that's where you're going to be interpreting your JavaScript. That's where you're going to be decoding your media if you're doing software decoding. And so you just stuff that into the smallest sandbox possible. So then we can go and look at this picture again. And so when it says namespace sandbox up there, then that is a user namespace. Basically, what I don't think this line is very good in this box, but basically it says on this system, I can create a user namespace unprivileged. And remember what I said is that if you can create a user namespace unprivileged, inside of that namespace you are root. And then suddenly you can create stuff that you need privilege to create, like a PID namespace and a network namespace. So if you try this out, like sit down and want to do some C, then that's something to be aware of. Like if you pass only a PID and a network namespace flag to clone, it will fail. You need to be able to create the user namespace. So it basically says that's possible. And it also said it succeeded in creating a PID namespace, it succeeded in making a network namespace, it succeeded in making a seccomp BPF sandbox, and also to do that with tsync. Then it also says that Yama LSM enforcing is on. Now I'm not going to talk so much about that, but that becomes that's more interesting with regards to more of this internal threat. So one of the things that you will see both on Windows and Linux and many other different operating systems is that processes need to be debuggable, right? So you need some way to attach your debugger to inspect the memory, to be able to set breakpoints and do all of these things. And these, to be able to debug a process requires very powerful system APIs. Because you're basically outside of this process, but you're allowed to go and inspect the memory of this process. You're allowed to manipulate its execution. This is very powerful APIs. And that's good for debugging. But it's pretty bad for keeping secrets. Because now if you have some kind of malware on your system, then it can use the same APIs to go and fish secrets out of your memory, right? And so Linux has been spending a lot of time making these LSMs, Linux security modules, to try to enforce more of those kinds of security policies. And they're very much based on these internal threats. So something already running on your machine. If you want to dig more into this, I spent a lot of time reading Chromium and kernel source code. Linux man pages is awesome, lwn.net. Also, Michael Karisk is an awesome trainer and author. He wrote the Linux programming interface, and he often does training in Norway. So if you want to learn more about low-level Linux programming, he's awesome, and the book is awesome. He also has a course that goes specifically into Linux security and isolation APIs. And there he also goes more into C groups. So if that's something that you find interesting, then that's definitely something to look at. And that's my talk. So thank you very much. Okay, so any questions? If not, you can come down here after. Yes? I think more or less everything, but you will have different kind of APIs. Like what you will see. Oh, sorry, I should repeat your questions. Do you have equivalent security mechanisms used in Chromium for Windows? And I think the high-level goals of the sandbox is the same, no matter what platform you're on. But it also depends on what is available on your platform, what is used to actually construct the sandbox. So the process architecture is the same, and the security concerns are the same. So a lot of the problem domain, it maps. But what you see generally in Chromium is that most of the code is cross-platform and runs on all platforms. And this is kind of interesting because you will have things that normally you would only use on Linux, but they decide, oftentimes they'll pull in the library only on Linux, and after a while they'll decide we're going to have this everywhere because it's easier. And so you'll end up with like, okay, so we're going to do the font handling using this open source library, and we're going to be using it across all of the platforms. And very often that is what you see inside of Chromium. But when it comes to this part, it's almost all of it is platform specific. So it's very, very little that is common. because it's using native functionality. I'm not sure that answered your question. Yeah, okay, good. Any more questions? Okay, thank you.